Binary inside a computer, how bits represent data and instructions. Introduction. In Part 1, we learned how binary numbers work. Binary uses only two digits, 0 and 1. We also looked at bits, bytes, powers of 2, unsigned integers, and basic binary addition. But this leads to a much more important question: how can the same zeros and ones represent numbers, letters, images, memory addresses, and CPU instructions? The answer is one of the most important ideas in computing. A computer stores patterns of bits. The meaning of those bits depends on how they are interpreted. In this video, we will look at how binary is actually used inside a computer. Chapter 1. A computer stores bit patterns. Consider this 8-bit pattern, 01000001. What does it mean? If we interpret it as an unsigned binary integer, it represents decimal 65. But that is only one possible meaning. In ASCII, the exact same 8 bits can represent the capital letter A. They could also be part of a CPU instruction, part of a memory address, part of an image, part of an audio sample, or simply one byte inside a file. The bits themselves do not contain labels. They are just a pattern. The meaning comes from context. Chapter 2. Binary inside CPU registers. A CPU register is a very small and extremely fast storage location inside the processor. A 32-bit register stores exactly 32 bits. For example, 000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 1101. If we interpret this pattern as an unsigned integer, it represents decimal 13. But the register does not store the characters 1 and 3. It stores only the binary pattern. The CPU's arithmetic and logic circuits operate directly on those bits. A 64-bit register works the same way, but it can hold 64 bits instead of 32. Chapter 3. A register does not know what its bits mean. This is a very important concept. Suppose a register contains 000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000It might use it as the character A. It might be a memory offset, part of an address, a bit mask, or an instruction operand. The physical register does not know which interpretation is correct. Software and CPU instructions determine how the stored bits are used. This principle appears everywhere in computing. Chapter 4. Binary inside memory. Main memory, or RAM, also stores binary information. Conceptually, we can think of memory as a very large collection of bytes. Each byte contains 8 bits. For example, 3 consecutive bytes might contain 01000001, 01000010, 01000011. If we interpret them as unsigned integers, they represent 65, 66, and 67. If we interpret them using ASCII, they represent A, B, and C. The physical memory does not know that those bytes form text. It simply stores bit patterns. Software gives those patterns meaning. Chapter 5. Memory addresses are binary too. Every location in memory needs an identifier. That identifier is called a memory address. Memory addresses are also binary numbers. For example, a simplified address might be 00010110. That is decimal 22. Real computer addresses are much larger. A 32-bit system uses 32-bit addresses, while a 64-bit architecture can work with much larger address values. The important idea is simple: the address used to locate data is represented with bits, and the data stored at that address is also represented with bits. Chapter 6. Binary and text computers must represent letters and symbols as numbers. One important early character encoding is ASCII. For example, A equals 65. B equals 66. C equals 67. Decimal 65 in 8-bit binary is 01000001. So the character A can be stored as 0100000001. That is the basic idea behind storing text as binary data. Chapter 7. Modern text uses Unicode. ASCII is useful, but it supports only a limited set of characters. Modern computers need to represent many languages and symbols. That is why modern systems use Unicode. One of the most common Unicode encodings is UTF-8. UTF-8 uses one or more bytes to represent a character. Many English letters use 1 byte. Other characters may require several bytes. But the basic principle does not change. Characters are encoded into bytes, and bytes are stored as bits. Text on the screen eventually becomes patterns of zeros and ones in memory. Chapter 8, Binary and Images. Digital images are also stored using numbers. A color image is made of pixels. A common pixel format uses red, green, and blue components. If each color component uses 8 bits, then each channel can have a value from 0 to 255. For example, bright red can be represented as red equals 255. Green equals 0. Blue equals 0. In binary, that becomes 11111111000000000000000. So 1 pixel can be stored as a collection of bits. Millions of pixels create millions of numerical values, and those values become the image we see. Chapter 9, Binary and Audio. Digital audio works in a similar way. A microphone converts sound into an electrical signal. The system measures that signal again and again. Each measurement becomes a number called a sample. So the process is roughly, sound becomes an electrical signal. The signal becomes samples. The samples become numbers. And the numbers are stored in binary. An audio file is therefore a large collection of binary values that describe sound over time. Again, the computer stores bits. Software interprets those bits as audio. Chapter 10, Binary and CPU Instructions. Computer programs must eventually become instructions the CPU can execute. A processor does not directly execute source code such as A equals B plus C. Instead, the program is translated into machine instructions. Machine instructions are encoded as binary patterns. A simplified instruction may contain several fields. One field may describe the operation. Other fields may identify source registers and a destination register. Different processor architectures use different instruction formats. But the basic idea is the same: a machine instruction is a carefully defined pattern of bits. Chapter 11, Binary selects CPU registers. Suppose a processor has 32 registers. How many bits are needed to identify one register? 4 bits give only 16 combinations. That is not enough. 5 bits give 32 combinations, because 2 to the 5th power equals 32. So 5 bits can identify registers numbered 0 through 31. For example, 00000 can mean register 0. 00001 can mean register 1. 01000 can mean register 8. 11111 can mean register 31. This is why a processor with 32 registers can use a 5-bit register field. Chapter 12, Binary fields can control hardware. Binary values are not only data. They can also control hardware. Inside a CPU instruction, some bits may select registers. Other bits may tell the ALU what operation to perform. A simplified control field might use 000 for ADD, 001 for subtract, 010 for AND, 011 for OR. Real processors use more complex encodings, but the principle is the same. Bits can represent both data and decisions about what the hardware should do. Chapter 13, Signed and Unsigned values. The same bit pattern can represent different numbers depending on how it is interpreted. Consider 11111111 as an unsigned 8-bit integer. It represents 255. But in the most common signed representation, called 2's complement, the same pattern represents -1. The physical bits did not change. Only the interpretation changed. So 11111111 can mean 255 or -1, depending on how the CPU and software treat it. Chapter 14, Why negative numbers need a rule. Binary naturally represents positive numbers, but computers also need negative values. One simple idea would be to use 1 bit as a sign. But modern processors usually use 2's complement. For an 8-bit signed integer, the range is -128 to +127. For example, 000000001 means positive 1. 11111111 means negative 1. 2's complement is useful because the same binary adder can perform much of both signed and unsigned arithmetic. We will cover 2's complement in detail in a separate video. Chapter 15. The same bits can mean different numbers. Consider 1000000000. As an unsigned 8-bit number, it represents 128. As an 8-bit 2's complement signed number, it represents negative 128. The bit pattern is exactly the same. Only the interpretation is different. This gives us a general rule: bits have no meaning by themselves. Meaning comes from how they are interpreted. Chapter 16. Binary and hexadecimal. Binary is ideal for computers, but long binary numbers are difficult for humans to read. A 32-bit binary value can easily become a long string of zeros and ones. That is why programmers and hardware engineers often use hexadecimal. Hexadecimal is base 16. It uses the digits 0 through 9, followed by A, B, C, D, E, and F. The key advantage is that one hexadecimal digit represents exactly 4 binary bits. That makes conversion between binary and hexadecimal very easy. Chapter 17. Why hexadecimal fits binary so well. Consider this binary value: 1101, 1110, 1010, 11011011, 1110, 1110, 1111. We can divide it into groups of 4 bits. 1101 becomes D. 1110 becomes E. 1010 becomes A. Continuing in the same way gives 0xDEADBEEF. The prefix 0x is commonly used to indicate hexadecimal. Hexadecimal does not change what is stored inside the computer. It is simply a more convenient way for humans to write binary values. Chapter 18. Binary inside the CPU. Datapath. Now we can connect these ideas to the processor. Suppose the CPU executes an addition instruction. The machine instruction itself is stored in binary. The CPU reads the instruction. Some of its bits identify registers. The register file outputs binary values. Those values travel to the arithmetic logic unit, or ALU. The ALU performs binary addition. The binary result may then be written back into a register. The flow is machine instruction, instruction decode, register file, binary operands, ALU, binary result, register write back. At every stage, the processor is working with binary signals. Chapter 19. A simple CPU example. Imagine register 1 contains 00000101. That represents decimal 5. Register 2 contains 00000011. That represents decimal 3. The CPU sends both bit patterns into the ALU. The ALU adds them and produces 00001000. That represents decimal 8. The CPU can then store the result in another register. From a high-level programming view, we simply see 5 plus 3 equals 8. Inside the hardware, the operation is performed using electrical signals that represent binary values. Chapter 20. Instructions are data. 2. There is another important idea. A machine instruction is itself stored in memory. That means instructions are also binary data. Memory can contain ordinary program data and machine instructions. Both are ultimately made of bits. The CPU knows which bytes to treat as instructions because program execution follows a defined sequence of instruction addresses. This is one of the central ideas of a stored program computer. Program instructions and program data can both be stored in memory. Chapter 21. Does a computer really understand binary? People often say, computers understand only zeros and ones. That is useful shorthand, but it is not literally what happens inside the hardware. There are no tiny printed zeros and ones inside a processor. Instead, the hardware contains physical states such as voltage levels, electrical charge, and transistor states. Engineers interpret those states as logical values. For example, low may represent 0. High may represent 1. Binary is an abstraction that allows very complex digital systems to be built from simple logical states. Chapter 22. From physical states to software, we can think of a computer as a stack of layers. At the bottom are physical electronic states. Above that are bits. Bits form bytes. Bytes can represent numbers, addresses, and instructions. Above those are programs and applications. A programmer may write, int x equals 10. The programmer does not normally think about individual transistors. But many layers below that line of code, the hardware is storing and manipulating bits. This is how software and hardware connect. Chapter 23. Binary connects software and hardware. Suppose a program contains the value 42. A compiler may place that value into a machine instruction. The processor may load it into a register. In 8-bit binary, 42 is 00101010. The ALU may then perform operations on that bit pattern. So the path can be simplified as source code, machine instructions, binary, registers and memory, digital circuits. Binary is one of the most important layers connecting software to hardware. Chapter 24. One pattern, many possible meanings. Consider one final example, 01000001. Depending on context, it might represent the unsigned number 65. It might represent the ASCII character A. It might be part of a machine instruction. It might be image data. It might be part of a memory address. Or it might simply be one byte inside a file. Nothing about the bits themselves tells us which interpretation is correct. The surrounding system provides the meaning. Chapter 25. The core idea. If there is one idea to remember from this video, it is this: computers store patterns of bits. Those bits gain meaning only when hardware or software interprets them. A computer does not fundamentally store the letter A. It stores bits. It does not fundamentally store a photograph. It stores bits. And a CPU instruction is not stored as an English word such as ADD. It is stored as bits. The bit pattern stays the same. What changes is the interpretation. Conclusion: binary is much more than a way of writing numbers with zeros and ones. Inside a computer, binary patterns can represent integers, negative numbers, characters, memory addresses, CPU registers, machine instructions, pixels, audio samples, files, and network data. CPU registers store bits. Memory stores bits. Machine instructions are encoded as bits. Even control information that tells hardware what to do can be represented by binary fields. Most importantly, the same bit pattern can have different meanings. 01000001 can represent decimal 65 or the character A. 11111111 can represent and sign 255 or sign -1. The bits do not change. The interpretation changes. This is one of the most fundamental ideas in computer architecture. Computers do not inherently store numbers, letters, pictures, or instructions. They store and manipulate patterns of bits. Once you understand this idea, topics such as CPU registers, machine instructions, memory, data types, hexadecimal, and computer architecture become much easier to understand. The next useful topic is 2's complement, which explains how modern computers represent and calculate with negative integers.